We're talking about the electron structure, correlations, and non-fermi liquid scattering in layered nickelates and cuprates. More of the time will be on cuprates. Nickelates will be at the end. These are layered nickelates. They are not superconducting, but there's a lot of new information from the ARPAs. And so I'll be talking about not just the electron structure, but especially the electronic self-energies. We're working very hard to turn ARPAs into what I'm calling a self-energy spectroscopy, where we get scattering rates, mass enhancements, and versus frequency, temperature, momentum, doping, etc. Yeah, so this is our campus. Here, this is our backdrop. I should comment, with so many people here from Flatiron Institute. These things here, I would say, are the original Flatirons. Each of these guys here. Flatirons. It's actually a guy skeeved out one of these 2 years ago. Look at this. Okay, and the main team, few of my grad students and postdocs. These are, we're both doing cuprates and nickelate work here. The cuprate samples, Dessau samples came from Helmut Berger and from Dennis Blue's group. And the new layered, these are triple layer nickelate samples from John Nichols' group that are done. Okay, so these are the 3 topics for our ARPA's measurements. I'm going to start with the nodal electron normal state scattering rates in cuprates. There's what we show is our power law liquid scattering rates. So we're all very familiar with the linear and omega and T scattering. We argue this is only linear at optimal doping, sublinear for underdoping, and beyond linear, supralinear. Eventually, of course, we understand extrapolating to quadratic from liquid light. Talk about this Planckian scattering, non-quasi-particles. There's a lot of excitement about this SYK or the Tayev model that maps very well to what we're finding. So this is nodal, and this is just normal state. Then I'll move into a self-energy analysis across the entire Brion zone, and including the normal and simulated state. We need to go beyond these one-dimensional MDCs and EDCs, or momentum distribution curves and energy distribution curves. That's been the mainstay for the past decades of ARPA's analysis. And so we go to a true two-dimensional thing where everything happens together, and this is really where I'm talking about ARPA now evolving into a self-energy spectroscopy. And then I'll talk about these nickelates. We call them the 4-3-8 tri-layer. There's 3 nickelates here, and these are very close analogs to the cuprates. The same diaxial minus y squared orbitals is similar from surface topology. We don't seem to have this extra 5D electron pocket in these, but they haven't been taken superconducting yet. It's very hard to dope them away. They're basically line compounds. Okay, so let's see. It's ARPAs. I don't need to spend too much time for this group here, but very quickly, photon in, electron out. We know the energy of the photons. We measure the energy of the ejected electrons through kinematics, measuring the angles, etc. We can get band positions as a function of kx, ky, kz. So what most people on the computer are doing is they're doing band mapping or peak tracking. You know, you watch this version and say that's a Dirac point. We've been working very hard over the last number of years to go much beyond that, to really get at the band broadening and band renormalizations, and all this is contained in the spectral function. And for this group, again, you're very familiar with this, really after the self-energy, signal prime, the real and imaginary parts. Basically, the imaginary part broadens it, the real part shifts, or renormalizes the band energies. This would be Lorentzian if the self-energy, sigma prime, double prime, were not frequency dependent. If there was no omega dependence, that's Lorentzian. That's sort of what you expect for a lifetime broadening. But with an omega dependence, as there is in these solid-state systems, these get distorted, and that's one reason really understanding these has been very difficult. Okay. Let me move forward to the nodal normal state scattering and cuprates. This is Bisco, is the famous favorite material for spectroscopy recuperates, largely because of beautiful cleaves. So here's your Briand zone, here's your Knowles electrons, so the D gap is largest here. These have the largest Fermi velocity, they dominate the transports. We heard this from Louis yesterday, similarly. So this is an ARPES measurement along this green cut here. So energy versus K, here's the Fermi energy. And dispersion in this guy would come way down here as some sort of parabolic band. We bring your Fermi energy. This is raw data. And in this case, it's fair for me to use just MDCs, and that's because dispersion is very linear. I won't do this. Change your 2D spectroscopy that I'll talk about after this. And so the measurements here, we're just taking many cuts, and we're looking at the widths of these, delta K of these MDCs in inverse angstroms. You can see it's sharper here, broader here, sharper, broader. You might think it looks linear here and looking quadratic here. I want to say that's not really don't believe the proper way to look at this data. I'll tell you more about that. Anyway, this is one cut at one temperature, one sample. Now here's many different doping levels, from underdoped, optimal doped, overdoped, at many different temperatures, and then there's many families of these put together. Okay. At low temperature, there's lower scattering rates, or lower sigma double prime, or lower momentum widths of these types of momentum. Okay, so you take the momentum width, you multiply by the bare Fermi velocity, and you get sigma double prime. So all of this is in the normal state, because I don't want to worry about the effect of superconductivity. I'll do that in the next set of slides. So there's a full family here, and in black dashed are fits to these. I'm not fitting any one curve separately. I'm putting everything simultaneously, the entire family. And the fits are quite good, and I'll show you more details about that. So there's many more constraints on me fitting the whole family together, and this, I think, is the first time this has been done in ARPES. Let me show you what we fit to. We fit to an ansatz for what sigma double prime should do. We call this the power law liquid phenomenology. So as a function of frequency or temperature, it's sort of an internal quadratic thing, but then raised to some exponent. That's our power law. And with something that connects the two scales, an offset, a coupling term, and then I'll tell you about this later. Here's the data, which is the same as on the last slide. So again, I put everything together. Let's just pick out, say, optimal doped sample. So this is our standard max TC curve. So the green is TC. Here, I would pull an alpha term of 0.5. Okay, so something squared to 0.5 is linear. Something squared to 0.5 is linear. So it's linear in omega and linear in T, both. Okay, I'm measuring in omega and in T, both, and that's all simultaneous. Okay, and you can see for the many different samples, many different dopings, there's different families of this evolution. So let's look more closely. This beta thing that couples omega and T, that's scattered around pi. Okay, theoretically, for a Fermi liquid, beta is supposed to be pi. And these are not Fermi liquids, but that's expected from Matsubara analysis working in that time. Okay, so that's just from the fits. That's not enforced. Lambda, this coupling thing that says, okay, it's linear in T or something near that. Well, how fast does it go linear in T? That's my coupling parameter, lambda, and coupling parameter. I find that's essentially doping independent at 0.5. And this is basically this Planckian dissipation, but more details on it. This is a very pleasant surprise for that this is so constant. And then everything else just comes linear. This key thing then is alpha. That's the thing that's varying. I already showed you that goes to 0.5. If you extrapolate to much higher dopings, eventually, imagine this might come to 1, and that would be a Fermi liquid, quadratic in omega, quadratic in T, scattering. There's a gamma naught, some impurity scattering. I already showed you where those are in the data. Those do bounce around a little bit. It's an offset. Yes. Excuse me? Omega N, great. That was the last thing I was going to say. This is, okay, first of all, this is here to make my units work. Okay, because this is energy, omega, H bar omega. This needs to be energy, but as this alpha varies, I need to keep this in energy units. So omega N is something we put in, and we put it in as a very large number. I think it's 0.5 eV for us, but it essentially drops out. Let's just go to the case alpha is 0.5. 2 times 0.5 is 1, minus 1 is to 0, completely drops out there. Okay, I mean, something to keep the units right, and we've tried a variety of values. It does matter a little bit here and here, but only very weakly. Yes. There is a little bit of coupling there. Okay, so we have all this data from many temperatures, many frequencies, etc. We scale them according to this thing inside here. And I call that thing inside C squared. There's a thing inside for the different dopings. And all the different temperature curves here now fold onto one set of lines if I do a log plot. And the log plot, we know the slope of this is the power law exponent. And so the many different cuts, you see they're overlapping here, but they all fall on the same line. And you see the slopes with my alpha varies smoothly from overdose to optimal dose to underdose. So it's about 0.5. Okay. So that's what the data shows. Here's just seems what it like. Use that formula, this I call this power law liquid formula, to take it to the various limits. Here's limit alpha equals 1. That's pure quadratic. And this is what you expect here. Sigma double prime, the scattering rate goes quadratically. This is the alpha equals half. This is the linear in omega, linear in t. And I'm just plotting what I expect from the double prime to do versus frequency. This is 100 Kelvin. And the plot is the red guy. You would say this looks linear and this looks quadratic. You might think that means that this is firmly liquid-like, but it's not. It's explicitly linear. And we get this S-shaped thing here for the underdose region. Again, it looks sort of quadratic-like and looks sort of linear-like, but so looking at one portion, we would argue, is not sufficient to understand these forms. Of course, with this form of the self-energy, I can plot versus any doping now. Remember, the power law exponent is linear in doping, so these are different doping levels. I can plot versus temperature. And here's sigma double prime at omega equals 0. And here's the family I get from overdosed to near optimal, because optimal is fully linear, and then underdosed. And with these, and then we also measure from velocities and whatnot around the Fermi surface, we can calculate the resistivity using a certain number of approximations, either a Boltzmann type model, a computer type model, and see the calculated resistivity from the ARPES, and this is measured resistivity. I want to comment the scales here are the same. This is 1,000 microohm centimeters. This is the same temperature scale, and these are roughly the same doping ranges. And so, while not perfect, I think it's very satisfactory. Maybe surprisingly good. Okay, so I think I want to move a little forward. Okay, so with this, we can also calculate optical conductivity. This is done at 300 Kelvin. So this is sigma 1 versus wave number. This is at 300 Kelvin for different dopings. Here, it looks like there's some Buddha-like peaks, but it's not, they're not real quasi. It's not from liquid. And compared to experimental measurements of the same, again, with the same scales, 2,000 and 8,000, etc., and the doping levels. So you might think these are to life or something. But if I take my formula and go exactly to temperature 0 and frequency 0, I can actually directly extract the quasi-particle residue. And below 0.5 in the underdose is precisely 0. You know I have spectral light things in my ARPES data. There is a quasi-particle residue, but I would not call these Fermi liquid or anything like that. The Fermi liquid limit would only be way out here. All right, I want to move to my next. Okay, so last comment. So this is called power law liquid. I would like to call this a quantum critical phase rather than a quantum critical point. Everywhere we're looking in doping, there's this behavior very smoothly. And so some of this type of physics may be going on in some of these models. And of course, superconductivity born out of these states. So we want to try to understand this, our community understand this in detail. Okay, let me move to the next set of data and analysis. So across the entire Brion zone. And let's see, in the nodal data, the dispersion was very linear. It's easy to do the analysis I was discussing. As we move around the Brion zone, especially towards the antinode, the spectral dispersion gets no longer linear. There's a lot of curvature here. There's a lot of running. The self-energies get large, and the community's had a hard time how to deal with it. So this is from Zietshen's work back in 2004. He shows you if I take external data, this is in the simulated state of Dessau. If I take EDC cuts in red, I get this kind of dispersion here. If I take MDC cuts and look where the peaks are, I get this type of dispersion. Qualitatively, they're extremely different. And so then we're trying to use this and try to get velocities and gap values and whatnot. It's very difficult. So this is where the state of the art was until this past year, where we realized we need to go beyond 1D analysis and do a full two-dimensional analysis, deal with both MDCs and EDCs simultaneously. And from this, we obtained the bare band dispersion, gaps, and a fully causal self-energy. We get sigma prime and sigma double prime simultaneously. So we're getting these details with one particle electronic interactions. We're actually doing it with fits that have orders of magnitude fewer free parameters. Okay, so here's ARPES data. I'll show you more details where this comes from, but this is in the simulated state on a TC85 sample, somewhere in the mid-zone. This is superconducting gap here, and this color scale stuff, this is fit to this data. Okay, what goes into the fit? Well, there's a bare band shown in red dots, a parabolic thing, which is here, and basically what we're fitting to is this Namu-Gorkov-Green's function. So here's the bare dispersion, epsilon k. Here's the self-energy, and here's the carrying terms, okay? And the ARPES, we're looking at the spectral function, which is the imaginary part of G11, this guy. And of course, phi is the gap renormalized with this parameter z, which is 1 minus sigma pi over this is a resolution function that we can independently determine. And so we can evolve with the resolution function while we're doing the test. Okay, the data I previously showed you in the last slide was this data here. All experimental data and fits is one part in the Brion zone, so there's a minus KF and a plus KF. And here's many temperatures, all on that one fit, on that one slice, I'm sorry. And let's see, to do this, I already showed you we need to extract a bare band, which is this parabolic thing. And here I show you for all the temperatures, the bare band we extract is the same. Okay, we didn't force that, we found that. Okay, and because it's bare, it shouldn't care about the temperature. You can see as you warm up, as you go across TC, which is around here, these spectral features are quite broad. So there's, okay, so okay, thank you. There's lots of broadening, so sigma double prime at high temperatures is large, especially at deeper binding energies with a Fermi energy here. So let me show you, let's say I'm at 50 millivolts, somewhere around here. I'm at 200 K. My sigma double prime is over 100 millivolts. That's definitely non-quasi-particle-like. Okay, but at low temperatures in the region and low frequencies, I have a drastic dropping of sigma double prime. Along with that, I have a peaking in sigma prime, and this happens because of causality, because of Palmer's-Kronig. And these are constraints that go together. Okay, so maybe this is one of the main messages. As I go through nothing, I have a huge drop in sigma double prime. Of course, there's a gapping of the spectral weight as well. These are the sigma prime and sigma double prime as a function of temperature and frequency that make each of these fits that are all working extremely well. I can do this. Well, those are 2D fits. If I look at 1D lines of EDCs or MDCs, the red is the external data, the black are fits. They're not perfect, but they're actually really good. They're better than I could do from a single EDC or MDC because of the asymmetry. If I try to fit this asymmetric thing with a Lorentzian, as I typically do, I have problems. I need to put an artificial background in. That doesn't come here. And I have orders of magnitude fewer free parameters. So we're very happy with how this works. We do it as a function of momentum throughout the Brion zone. Here's near the node. The self-energies are much smaller. If I go to the anti-node, the self-energies are huge. Here's 300 some millivolts at 50 some millivolts. So that's huge sigma double prime compared to energy, extremely non-quasi-particle-like. Along with that is a huge effect on sigma prime. This gives these kinks and whatnot, and extremely flat bands. So my time is a little tight. I can say what we observe is as a function of temperature, there's a transfer conversion of this huge sigma double prime to a sigma prime, to from an incoherent thing to a coherent thing. That starts slightly above TC at about a pairing temperature, about some 20 Kelvin above. And there's details of this. We believe it gives positive feedback onto the pairing that can help strengthen pairing mechanisms, but more work needs to be done on this. Okay, in the last few minutes, I want to go to the nicolates. And so let's see, we are working with also hydrogenated samples. They start as single crystals of a 4 through 10, 3 nickel oxygen layers. John Mitchell, who works with us, is able to remove oxygen, go to the 438. It's a line compound. If you just count from valences, you expect the doping level would be here, slightly overdosed, something like 8.67. Okay, and I'm overlaying that on the cuprate doping phase diagram. Here's RBES on it. These are Fermi surfaces and cuts slight 100 millivolts below. We're using 2 photon energies to pick out various parts of the electron structure. You can see sort of like hole-like things here, electron-like things here. We put them all together, and this is what we get. And I'm comparing to an overdosed disco Fermi surface with bilayer splitting. Here there's trilayer splitting. So there's a dashed one here that's hard for us to explicitly resolve. And here's DFT of this, again, 1, 2, 3 of these bands, because it's a triple layer nicolate. And that's very similar to cuprates, if you like, nodal and antinodal states. I can go into more detail and show you the E versus K. This is not yet published. So cut 1 is along here. Cut 2 would be like your nodal cut. And then cut 3 would be like antinodal. So here's the raw data. These red lines are fits to the peak position through the data. These are just MDCs for now. That dispersion is shown here, experimental dispersion, and I overlay that with the DFT. Okay, so you can see KF matches extremely well, like you'd expect in your type of liquid type thing, your volume from surface volume, but the masses are heavier in the experimental data. And that's sort of what we are used to from cuprates. Let's see. I can do symmetry analysis by varying my photon polarization from P to S. There's details about this using mirror planes and whatnot. The upshot is you find that this is dominated by the dx squared minus y squared states, and then also what the DFT shows. Let's see. Last slide is on scattering rates. This is called the nodal cut. This is the experimental data, sigma double prime versus frequency. Here's the Fermi energy. The yellow squares are the experimental data. And I fit this to either a Fermi liquid type of analysis, doesn't do such a great job. Marginal Fermi liquid at 0 temperature would be perfectly linear, but I'm at finite temperature, I'm at 22K. And that is the black dashed lines which fit quite nicely. Okay, so sort of a linear thing here, and quadratic-like if you like, but really just marginal Fermi liquid all the way. And here's transport data, normalized resistance versus temperature. Now, this is versus frequency, this is for temperature. It's not really arbitrary because I know how to connect them with this beta term, or roughly pi. A t squared of this scale is roughly omega squared on this scale. So roughly the same. And again, I just compare the quadratic and the linear, and you can see the scattering rates are quite similar between them. Okay, I think this is my last slide. Thank you for your attention.
All right, let's dive right into the questions. I'll repeat the questions while and then
okay.
Harold.
Yes.
Okay, wait, so the question is about the filling level of the inner layer versus the outer layer.
They're certainly different. The two outer layers, there's one filling level, okay, from the DFT. And I don't remember the full details, but they're definitely different. And yeah, I don't want to say where it is now. We've looked at it, I just don't remember the full details. But from what we can tell, because the ARPA's Fermi surface closely matches the DFT Fermi surface, I think volumes, et cetera, I think probably correct.
In the back. Okay, so the question is about the quasi-particle pole and quasi-particle residue, and what happens when you don't have a single pole. How do you define that?
Right. So analytically, we can access this also numerically, but there is no pole here. There is no residue. It's a branch cut. Yeah. So there is no pole. That's why alpha is 0. There's still some peakiness to the spectra. I should say, if you go away from t equals 0, you go to 1 millikelvin. This is now finite. Calculate that, and I can sit down with you. I can show you details. And it's worked out in detail in the supplementary materials of yeah. Yes, but there's one parameter that really dominates. Yes.
Okay, wait. So what's the question? The question is it a 4-parameter fit? Okay, so the question is what other 4-parameter fits were tried before arriving at the current one?
So, well, the main thing we tried in comparison was going to do a superposition of a linear and a quadratic. And this has been used in literature. We found that did not work so well. It's especially difficult for us to get the S-shaped conductivity here. No, I don't think it is because there's parameters in each of those in the fermi-liquid part and the marginal fermi-liquid part. There's perimeters in each of those, and then a weighting. Of course, I cannot say that we're not exhaustive. Those are the main two that we looked at.
Okay, one last
Could be something else.
one last question.
Yeah, okay. So there's two things you need. Cutoff.
Okay, wait, so the question is about Kramer's pruning, and what do you do because you need all frequencies?
Yes, yes. So first you need a cutoff that's some deep energy, and we go quite deep. We go well past the bottom of the band, which is about half a volt. If we go to half a volt or a volt, there's very minor differences. And then there's the negative versus positive frequency side. And we're only probing the negative frequency or the binding side. So we looked at, the first thing is symmetrize the scattering rates, not the electron structure, not the band dispersion. So we can symmetrize the self-energies. Sigma double prime should be even and sigma double prime should be odd. And then put some canting, one side versus the other, and look at a variety of possible cantings with basically form similar on both sides. We find we get the best results if it's symmetric. But this is all uncharted territory, so it is direct that we don't have full control of the unoccupied side of it. But the zeroth order, we find the best result if they're symmetric, and they're quite good.
Okay, great. Thanks, Phil. Let's continue this discussion with Harold and Dan during the break, and we are going to stop and have our coffee break now until 9:30.